Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to be looking at separators, and in particular, we're going to be looking at the design equations that can be used for simple ideal systems. So the Kremser and Colburn equations are very commonly used when you know A, the ratio of L to G, with the equilibrium relationship K. And if that's essentially constant, then you can use the Kremser equation for trade towers or the Colburn equation for packed beds. N is the number of theoretical stages, and in the case of the Colburn equation, it's based on the overall gas mass transfer being dominant. And so these are the equations that we end up using. And they relate the gas composition at the inlet and the outlet compared also to the ideal that you would have if it were at equilibrium. Now, in the book, they plot these, and the advantage of looking at graphs is not so much that you're going to want to read answers off of a graph, because after all, we can calculate these things, but you see trends when you look at graphs. So you see that the theoretical number of stages, as you increase the y out value or the x out value, is going to increase rather dramatically in some cases. And this also is related to how A changes. So for various values of A, then we end up with these various curves, and the shape varies dramatically. They do an example in the book, and it's a tray scrubber with 8 equilibrium stages that's operating with 40 kilomoles per hour of air and a mole fraction of 0.02 being reduced to 0.001. And the acetone is being absorbed using a 20 kilomole per hour water stream. Now, this is the way it is operating. The question is, and this is something that probably is different than how you've looked at these problems before. You have a process upset, and now then you need to increase the flow rate of the air, and they're saying if you increase the air flow rate by 10%, what's going to be the new outlet mole fraction of acetone in the air? And so they do that, and they use these graphs as a way of evaluating this. And I'm not going to go through all of the details, but basically what's happening here is they're coming in from the graph, and they were at this point here, okay? And now then with the new value, instead of A being 1.2, they're now at A equals 1.08, okay? And so they have to move to a different curve. Well, notice that means that they're having a different fraction of the y, which means a different y at the outlet. They then say, look at how this would vary for a wide variety of endless gas flow rates. So decrease by 20%, increase by 20%, and assume that everything else remains the same. And so they do that, and they created these graphs here based on the various values that they would have of A. So they've changed the gas flow rate, and the liquid flow rate needs to change correspondingly in order to have a similar value of A, right? L over G over the K, the equilibrium y over x. And so that's what they've done in this graph. And again, the advantage of creating graphs is that you learn trends. And I think we'll stop here, and we'll look next at the internal construction of distillation columns. So thank you very much for your time. Look forward to talking about the details of distillation towers. Thank you.